So hello everyone and welcome to today's class. Today we are looking at correlation analysis using R, and the objective of today's class is to describe the computation of both the parametric and non-parametric measures of correlation using R. In addition to this, we shall also be testing hypotheses to check for the significance of the computed correlation coefficients. So to start us off, let's look at the definition of a correlation coefficient. We say that a correlation coefficient is asymmetric. A correlation coefficient is asymmetric is a symmetric scale invariant. Symmetric scale invariant measure of association between two random variables. The word scale invariant here is key because it means that if you, for instance, divide the observations by a given value, and usually we prefer to divide by the standard deviation. If you take all the observations and divide by the corresponding standard deviation of the variables, then the correlation coefficient will not change because of that. I'll be illustrating that in a short while. Then we can say a few other things like that the correlation coefficient ranges ranges from -1, +1, with the extreme indicating perfect, with the extreme indicating perfect correlation, while 0 indicates no correlation. So what we're saying there is that a correlation coefficient is a number between -1 and +1. So if you want to represent that on a straight line, it is a value which falls within this interval, -1 and +1, including those two values. Then, so it means that it passes through 0. So this is what we are calling perfect. This would be perfect correlation. This is perfect. Then, if it happens that your correlation is at this point, this means that this is no correlation. Okay, then we expect there to be other values in between there. The other values in between there. So there are three main correlation coefficients, and we're going to discuss each one of them. And the first one is what we call the Pearson's correlation coefficient, or the Pearson's correlation. And the formula that gives us this is R of xy. I'm assuming that the two variables are x and y, is equal to covariance of x to y divided by the standard deviation of x multiplied by the standard deviation of y. Okay, so by definition, that's what we call the Pearson's correlation coefficient. And the formula is given by summation of xi minus x bar. Then this is yi minus y bar. Divide this by the square root of summation of xi x bar squared, multiply again by yi minus y bar squared. Okay, and we, as we said last week, is that this is a definition of formula. So we can recall that. If you take summation of x minus x bar squared, this is the same as summation of x squared minus n x bar squared. Using the same logic, you can express this one, y minus y bar squared is the same as summation of y squared minus n y bar squared. And also you can have summation of x minus x bar multiplied by y minus y bar. This is the same as summation of x y minus n x bar y bar. Okay, I guess these are things that you've come across elsewhere. So I'm just repeating myself. Yeah, so next we're looking at how to test for the significance of correlation coefficients. So briefly, I'll be talking about how to define the null hypothesis, and then the test statistic, and of course the distribution of the test statistic, which of course will be t statistic as we saw in our previous class. Then I'll mention the default level of significance that is used in R. But it's good for you to note that you can always adjust that level of significance to any other value that that you desire. So let's say that this can be done by transforming. This can be done by transforming the correlation coefficient to a t distributed variable. So basically we transform R, which is the correlation coefficient here, into a t distributed random variable. Okay, and you say under the null hypothesis, under this null hypothesis, that H naught, that rho is the population correlation coefficient, Pearson's correlation coefficient. So whatever we are having here, this is a sample correlation coefficient. Okay, so it's a statistic. So the population counterpart, so this is noted by R. So the population counterpart is denoted by rho. So we use rho. That's why we're using rho in our statement of hypothesis. And by default, we test the hypothesis that the correlation coefficient is 0. In other words, we are testing if the variables x and y are actually independent. So if they're independent, then their correlation should be 0 or not significantly different from 0. Okay, so then we say where rho is the population correlation coefficient, is the population Pearson's correlation coefficient. So that's what we are testing. It's a test of independence, if x and y are actually independent. Okay, then the test the test statistic is defined as these. So this item here, so you have R into n minus 2 divided by square root of 1 minus R squared. So this item here has a t distribution. New variable here, or variate, as a t distribution with degrees of freedom. Sometimes we denoted by v, is equal to n minus 2. Degrees of freedom, which we use, sometimes we use letter v to denote the degrees of freedom being given by n over 2. Okay, where n is the size of the sample. Okay, and then where r is the sample correlation coefficient. Sample correlation coefficient. you can mention that this hypothesis or the above hypothesis tests the null hypothesis, or just test the hypothesis, or test that there is no linear relationship. There is no linear relationship. There's no linear relationship between the variables. That is, rho is equal to 0, as indicated in the null hypothesis. There is no relationship. That means their correlation is 0. Okay? You say that this test is equivalent to, or this test is, you can say, identical to the test. It is identical to the test obtained from testing for the significance, testing for the significance of the slope coefficient, in regression analysis, or in the regression of, this happens only in simple linear regression, in regression of y on x, and vice versa in this case, or vice versa. So here it doesn't matter what is dependent and what is independent. But whatever the test here, it is equivalent to the one that we were testing on the slope coefficient beta 1 when we were regressing y on x. Okay, so let's see how we can implement this in R. So let's say we can implement this in R. Then we also see maybe the how not to do it, and then we also look at how to do it. So for correlation analysis, we shall be using this particular library later on. But I want to show you the effect of scaling, because we said that correlation does not change with the scale. So I want to see how that one happens using some other data set, not the one that we shall be using in this case. Okay, so I want to call some data here. The effect of changing scale on correlation. Coefficients. All right, so I want to use this data set. It's a data here which is called chemical reactions. I'm calling it chem_react. Now, this particular data set is in text file. Let me show you. So this particular data set is in .text format. It's not .csv. I know you are well familiar with the .csv format, but these are text file. So these values are saved in a notepad, as you can see. Yeah? So when you want to read such files, then you use the function that I've used here in R. So if you want to read a text file, like this is a .text file. So this is one way of reading it. I know there are other ways, but you can use this function, read.table. Okay. Then you write the name of your file. Of course, you are working within your working directory. Then if the first row of the file captures the variable names, you say header is true. If I don't say this, let me show you what happens. If I don't say that, I just put that. Then I say, that's my data. Then I say view my data. Then you will see that this is how it looks like. This is what you have, which is not quite good. So it reads like these are values, some observations, these ones, which is not the case. If you want to avoid that, you use header is true. So you come here and say header is true, or you can just say T, or I prefer to write in full. So when I do that, then I view again the data. This is how the data looks like. So you see now the labels go to the variable names, which is what I expected. Okay, so here we have some multivariate data set, which has a set of variables which we are calling Ys. So there are 3 Ys. So this is an example of what we call a multivariate data set. And then we have the variables of X. So basically, this is an example of paired data. So because we have this experiment, from that particular experiment, an experiment is just like an individual. So from the same individual, you take all these measurements. So these are paired observations, and so on and so forth. So there are 19 of them. So suppose I want to find the correlation. I want to find the correlation of this data set. So I need to calculate the correlation for all the pairs of observations. So I want to divide the correlation. I want to get the correlation matrix first. Then I want to divide each variable by the corresponding standard deviation. So in a way, I'll be trying to standardize the values or the observations here. Then with the standardized values, I will want to check the correlation coefficient matrix. You will notice that correlation will not be changing. And that's why we said that correlation is scale invariant. So even if I change the scale here, then correlation will remain the same in all the cases. So let's go back to R. So let me do this. R, let's see, this is the first correlation matrix. Let me call this R1. I just say core. Usually we use the core function to get the correlation matrix. Then I say my data. Okay. Then what do we expect? If I don't want to keep on having so many, if I want to run the code and show the output, you can put a bracket there and another bracket there. That means it will run the code and give me the output. Okay, so like that. Like that. So I need to remove, I should have removed the first column here because the first column is not a variable. So if I want to do that, I'll say my data. Then you come here and say open square brackets, comma, remove the first column. So if I type something here, it means that I'm selecting this row. Okay, but now I want to pick the columns column 2 to column 7 because column 1 is the ID, the experimenter. So instead of saying I want to pick column 2 to column 7, I can just say pick all the columns except the first column. So that's how I'm doing it here. Okay, that means that when I run the correlation coefficient, I don't expect to see these because this is not required. So I run this code here. So this gives me the new correlation coefficient is here. Yeah, so the question was about the function that we're using in line number 8. So this is a special function that you can use to read text files. Okay, if you are reading a comma separated file, you use the function read.csv. You read.csv, yeah. And there are many other functions that you can use to read different types of files. But if you're reading a text document like the one I showed you, which is in the data is in a notepad, which is that's why it's .txt, .text. You can use this. You can use this function read.table. Then, if you want the header to be the variable names, then you say header is true. Otherwise, the first row will also be considered like part of the observations, which is not actually what you want. Okay, then this is just to look at the data, how the data looks like. Then the objective of what we're doing here, we want to show that correlation is scale invariant. So what I want to do with this data, I want to divide every column, like let me show these. I want to divide, let's say, I want to divide every value in this column by the standard deviation of this variable. So I divide this by the standard deviation. Every value I divide by the corresponding standard deviation of that, or y1. Then I come here, I calculate the standard deviation of y2, and I divide everything here by that. So that is what we call changing the scale, and I'll be trying to standardize the values. I want to show that the correlation coefficient of the original data and the scaled data will be the same. But more importantly, I want to share with you a function that will help you to do that job quite easily, using a function which we are going to call the sweep function or the apply function. Okay, so I want us to note this correlation coefficient. This is the correlation coefficient of all the possible pairs of variables there. So you may not memorize all the values there, but maybe we may want to round the values. Let's say we may want to round the values close to 3 decimal places. So I can say round. I can say round the values to, let's say, 3 decimal places. And we run the code like that again. So we see. Yeah, that's okay. I'm rounding them off to 3 decimal places to make it look less bulky. So this is our first matrix using the original values. Then I want to divide every observation by the standard deviation corresponding to that particular variable. And I want us to look at a function which is called a sweep function. So maybe we can quickly search here and say sweep. This is called sweep function. So I want us to see what this function does. I don't know whether some of you have come across the apply function. Sweep function, is it here? No, the function is not here, but what about apply? Apply function. Yeah, so this is the apply function. As you can see, it has we have 3 main arguments inside the apply function. So the first one is the data set that we're talking about, or the variables that we're talking about. Then here you say whether you want to do whatever you want to do, either along the columns or along the rows. So if you want to perform the function along the rows, you'll put 1. If you want to perform the function along the columns, you put 2. Then here you say what you want to be calculated. So here you can say the mean, you can say var, and so on and so forth. So basically the apply function has these 3 arguments. Then when we talk about the sweep function, it's quite similar to this. It's quite similar to this. But there's a third argument where you put the formula that you want to apply. Once you get this statistic, then what do you do with it, with these values? Because this function here will just calculate, say, the mean, the column means. But suppose you want to divide every variable by the mean. So you need to come here and say you divide every column by the mean. So I'll be showing you that in a short while using the sweep function. So let's create a new data set. I'll call it my data dot standardized, and I'll use the sweep function. Yeah, I think the explanation is here. So I need to say the name of my data set. Then I say whether I want to do whatever I want to do along the columns. Then which statistic do I want to calculate? Okay. Then which function do I want to apply? Do I want to apply a division sign or a multiplication sign or an addition sign to the columns or to the rows and so on and so forth? So here I'll say sweep. Then open bracket there. I say my data. So that's my data. I want to work with my data, but of course without the first column. Remove the first column. Then I want to apply this along the column. So I'll put 2. If I were working along the rows, I'll put a 1 there. Then there's this, the stats. So what do I want to get from here? I want to get the column. I want to get the column standard deviations. So I can say apply for which data? For my data, except column 1, So that's my data. Then I say along the columns, so I'm putting a 2 there, then I want to get the variance. I want to get the variance. Okay. But of course, what I want to do, I want to divide everything. So divide every column, divide every variable by its standard deviation. That's what I want to do. So, but what I have here, this apply function. Let me try to work on it down here. So this apply function here, if I take it to the console here, there's a problem there. There's a question somewhere from Maxwell. All right, so I want us to dissect the apply function and see what it will be doing. And the sweep function will actually be working in a similar way. So this is the apply function that we're using. Apply my data, except column 1, working through the columns, get the variance. So this will give me the variance of every column in my data. If I run that code, these are the variances of all my variables. Just to verify that, if you say var of my data dollar, let me pick x3, which is the last one. It gives me 2.667, which is here. So we have successfully obtained a vector of all the variances of that particular data set, of all the columns. Okay, so the sweep function works in a similar way, because as you can see, there is this argument where you say, which data are you working with? Then are you operating on the rows or the columns? That's the margin. Then which statistic do you want to get for that particular data set? Here I'm saying the variance, but I want the standard deviation. So that means that I need to take the square root of these. I need to say square root of all these. I want to say the square root of these, all the way up to the end like this. So that's a sure way of getting the standard deviation. So just to verify, you can we can copy this and take it to the console just to verify in case there's an error somewhere. So you bring it here, then you enter. So you notice that these are now the standard deviations of the variables. Okay, so these are just square roots of these values. That should be easy to verify. Then the last thing in the sweep function is to say what operation you want to perform. Okay, so I want to see, yeah. And here you say comma, you say fun. Which function do you want to perform? The second one, this one, the one in caps. You say, and you put in quotes, you can say that is division. I want to divide every column by the standard deviation. Every column of my data, you divide by the standard deviation. You can say that. You can also put a plus if you want to add. Maybe you want to add the whatever is here. Maybe it's not variance. Or you want to, of course, this is in quotes, or you want to subtract and so on and so forth. So in our case, we want to divide everything, every column in this particular data set by the standard deviation. And to help you do that is the sweep function. So let's run this code and then we see what happens. I want to see my new data set. So I'll view, if I view my data standardized. So these are the standardized values. You see what the function has done. It has divided every column by the corresponding standard deviation. You can try a few because we have the original data. You have the original data, which is here. Like this value, take 41.5 divided by the standard deviation of this particular column. You will end up with these new values. Okay. So we want to show that if you calculate the correlation of these new observations, it will be exactly as the correlation of these older observations. So let's do that. So we can call this one R2, which is core of my data dot standardized, like that. Then I want to see the output at once. I also want to round off all the values. I want to round them off to 3 decimal places, just like the other one. 3 decimal places like that. Bracket is missing somewhere or what? But basically, a bracket was missing somewhere. So this is the function that will give us the new correlation values. I want us to compare R2 and R1. I want us to compare. I want us to compare R2 and R1. So where's my R1? Are these supposed to be R1, right? So I want us to have a look at now our R1, which is using the original data, and R2, which is using the standardized data. And these are the correlation matrices. As you can see, exactly the same thing. So that means that when you change the scale of the variables, then that does not change the correlation matrix or the correlation coefficient. Okay. Now I want us to go back to the basic things about correlation, especially how to, I think now we already know the function that we need to use to get the correlation. And then we also want to do a significance test of a correlation coefficient. So then we are going back to our original data, which is this particular data in the ISR, in the ISWR library. So this is the data we're using now. So I think now you have this data. I'll be sharing with you this data later on after the class. So this is the data that we have. I want us to perform correlation analysis for this particular data set. As you can see, we have some missing observation. So I want to see what are the consequences of such. So here we are going to use the core function like we have seen earlier on. Then we shall also be using the core.test later on to test for the hypothesis. Yeah, so I've attached the data to make it easier for me. Then I want us to use the core function for this particular data set. As you know, in this particular data set, there are some missing observations. So let's run this code and see what you're going to get. So if you run this, you'll get to return some warning, NA. So it doesn't give you the value, meaning that there's a problem somewhere. And that particular problem comes because of the missing values, So if you don't want to get these problems, we prefer you add these in the code. You say these, you add this optional argument. If there were no missing values, there will be no problem. So you say use in quotes complete observations like that. And now you can run the code. And when you run the code, you notice that the Pearson's correlation coefficient is this value here, 0.4167546. Okay, so it's good to be careful in case your data is missing values. You need to indicate that you want to use the complete observations. That means all the missing observations are left out. So that row is completely left out in the calculation, meaning that if there were 24 observations in the original data, that this new correlation here, or this correlation coefficient here, has been obtained using 24 in our case. I mean 23 values in our case, because one of them has been, this value here was not considered in the analysis. Okay. Then maybe a better way is to get this in form of a matrix, So you can say core. Then instead of extracting the column vectors, you just use the name of your data set. Okay, you just call the entire data set or data frame like this. Okay, then you may want to say use again complete observations. complete.obs. Okay, then you end up with a correlation matrix. So you can see this is a correlation matrix. So this is the correlation between blood glucose and short dot velocity, which is also the same value here. And then the diagonals are 1, just like any other correlation matrix. Okay. So this is much more interesting than using the earlier code here. It's much more interesting, especially in a case like the one that we have here, when you have several variables. When you have several variables and you don't want to pick all the possible pairs of observations, when you run a single line like this, and you put the name of your data here instead of the vectors comprising your data set, then you'll end up with something like this. Okay, where these are correlation matrix, the diagonals are 1, 1, 1 everywhere. And then the other values are correlation for the different pairs of observations. Okay, now how do we test for the significance of a correlation coefficient? Okay, so if you want to test whether the correlation coefficient is significant, you use core.test. Use core.test. Okay, then here we can say blood glucose, and then we have short dot velocity like that. And by default, this function here will use the complete observation. So I don't need to say it. So when you run this code, this is the kind of output you're going to get. The Pearson's product moment correlation. The data, we're using this variable and this particular variable. Then there is a t statistic. This is the t that you calculate using the formula that we defined in our slides. The one that converts R into a t. Then we have the degrees of freedom, which is n minus 2. Okay, n minus 2. And you can see here degrees of freedom are 21, though we know that our data had 24 observations, but it's good for you to note that this observation here was deleted when we are calculating the correlation. So this was not used. So 23 observations were used. So in that case, n is 23 minus 2. That's why we are getting 21. This is a p-value. The p-value corresponding to this t statistic. Okay. And you notice that this p-value here is similar to the one that we obtained. Actually, it is the same p-value we got for the slope coefficient when we ran the regression model for these particular variables. When we are regressing short dot velocity on blood glucose, then the slope coefficient was having this p-value, the same. So that's why we said in our notes that this kind of test is just similar to what we were doing in the case of simple linear regression. Then this statement here, of course, explains the nature of alternative hypothesis that you have. Of course, the null hypothesis is that rho is that the true correlation, that is rho, is equal to 0. Then the alternative in this case by default is that true correlation is not equal to 0, which is a two-tailed test. In case you want to work with a lower tail test or an upper tail test, you can always adjust in the coding. Then we have a 95% confidence interval for the correlation coefficient, which is given by this. Basically, this interval here does the same work that is done by the p-value, okay? Because basically you want to check whether this interval here, which starts from plus 0.005 all the way to plus 0.707, whether it contains 0 inside. In other words, is the 0.0 in between these 2 points? If 0 is found within these 2 points, then you conclude that the true correlation is not different from 0, because the 95% confidence interval or whatever percentage contains the 0 value. But if it does not contain the 0 value, it means that actually the true correlation is different from 0. It is equivalent to reject the null hypothesis that rho is equal to 0. So this interpretation here is actually it's just the same as this introduction. As you can see from here, the p-value is less than alpha, which is 0.05. So we're supposed to reject the null hypothesis. And that is also confirmed here because this interval here does not contain the 0 value. Okay. And then, of course, this is what we got earlier, the sample estimate, that is our R, 0.41675, which is what we got earlier on. So if you do this, I think we have done this already. Yeah, using this one, the same value, this value here, the same as that. So basically, that is how you check whether a correlation coefficient is significant, okay, using core.test. Any question before we move on? Yeah, so we mentioned in the background that if you want to change the confidence level, you use the conf.level. But a quick way is to just do if you query in R, you say core.test, then you run that code, you will see this. You will get this, a description of what that function does and the various arguments that are found in that particular code. So by default, you see that you need to put your X variable and your Y variable. Then you can say whether you want to, the kind of alternative hypothesis that you want to use. By default, we use a two-sided test. So you don't need to say it's a two-sided test. By default, it will be two-sided. But if you need a lower tail test, you will use this. Alternative is equal to less. Okay, if you want an upper tail test, you will say alternative is equal to greater. Then the method. There are three main methods which we're going to discuss. The default method is the Pearson. The Pearson correlation is by default, this function here calculates the Pearson correlation coefficient. But you can also calculate the Kendall's tau and also the Spearman's rho. So if you want these two, you need to specify that method is Kendall, of course in quotes, and then or method is Spearman, and you put the word Spearman in quotes. Then the other thing that you may want to change is this. If you don't want to use the default value or level of significance, which is alpha is 5%, you may change this. You may edit this. So those are the main things that you can change, especially this and the method, and possibly sometimes even that. So the others, you may want to keep them at default value. So for example, if you want to change to 99% confidence, this is the kind of code we shall be having. If you check my console down here. Okay. So, and then when you run this, if you run this code, you will get this kind of output. Okay, so this is Pearson's product moment correlation. Most of the stories will remain the same, but the alternative will change. The alternative hypothesis is that the true correlation is, sorry, this has not changed. What changes is the confidence interval. So this is now 99%. You can change it to 90% or any other percentage that you are interested in. Okay, so at this point, I want us to briefly look at the other measures of correlation, and these are the non-parametric methods, the Kendall's tau, and also the Spearman's rho. So we're saying that the Spearman's rho is, or the Spearman's rank correlation coefficient is a non-parametric measure of correlation, which is based on ranks. And the formula that we use there is rho is equal to 1 minus 6 multiplied by summation of d squared divided by n cubed minus n, where n is the number of observations, and then d is the difference between pairs of corresponding ranks. So that means that sigma d squared is the sum of the squared difference between pairs of corresponding ranks. For example, if you have some data set, let me say this is your x and this is your y. So you rank your x, and then you also rank your y. So here we have some values here. So let me say these are the ranks of x. The ranks of x, 1, 2, forget about the values. 1, 2, 3, 4, 5. Then I also rank y, so I get 3, 2, 4, 3, and 4. 3 and let's say 1. And this one should be 5. Something like that. So if this is my data and these are the ranks, you know what I'm calling D is the difference between these pairs, corresponding pairs of ranks. So D here is minus 2. Doesn't matter whether it's minus or plus, because at the end of the day I'll square them. So this is a 0. This is if this is a 3, then this is minus 2, this is a 1, and then if this is a 1, then this is a 4. Then I need to square them. You need to square them. So 4, 0, 4, 1, and 16. Then this summation, when you sum this column, that's what I'm calling summation of D squared. So D is the difference between pairs of corresponding ranks. Okay. So then, how do you do this in R? How do you obtain the Spearman's rank correlation coefficient in R? You use the same function that we were using up there. That is a core function. But now you must specify that the method is the Spearman's method. Should be the Spearman's method. Okay. Then, so that we can go to R once and for all, I also want to mention the other correlation coefficient, which is called the Kendall's tau. Yeah, so again, the Kendall's tau is also a non-parametric measure of association or correlation coefficient. And this correlation coefficient is based on counting the number of concordant and discordant pairs. We mentioned that a pair of points is concordant if the difference in the x coordinate is of the same sign as the difference in the y coordinate. Okay, maybe an illustration will make it more clear. And suppose we have two variables and we have ranked them from number 1 to number 8. Then we sort one of the variables, let's say y. We sort the ranks in one of the observations from the smallest to the largest. Then we leave the others unsorted or to be determined by the ranks of the first one. So when we talk about concordance, this is what we talk about. Okay. So starting from this value here, you ask yourself how many, you count, how many values here are greater than 3? How many values are greater than 3? So you count 1, 2, 3, 4, 5. So the number of concordant here will be 5. What about the number of discordant? Those are the number of values below this value here, which are less than 3. So you count within that interval. Notice that it's this one and this one. So you write here 2. When you come to the next value, you come to 2. And you ask the same question. How many observations, when you are here, how many ranks? This was supposed to be 4, right? Yeah, so how many observations below here are greater than 2? And it is 1, 2, 3, 4, 5, except this one. So there are also 5. Then how many are less than 2? It's only 1. Then you can also do it for this item here. When you're here, you ask yourself how many observations below here are greater than 1? How many are greater than 1? And in this case, it is 1, 2, 3, 4, 5. Again, there are 5. Huh? Then how many are less than 1? It's nothing. Then you come here. How many are greater than 4? 1, 2, 3, 4. So here will be 4. Then how many are less than 4? There's nothing. Then you come to the next one. How many observations are greater than 5? These 3. How many are less than 5? It's nothing. The same case, you come here. How many are greater than this? It's only 1. I'm sorry, they are not aligned. Huh? They are not well aligned. How many are greater than 7? It's only this guy. And how many are less? Only 1, this guy here. So you do that for all the observations. So then you need to count the number of concordants, and also these are the number of discordants. And the Kendall's tau will be the number of concordants minus the number of discordants divided by number of concordants plus the number of discordants, like that. So this is what will give you the Kendall's tau. And then we mentioned here that in scenarios of what we call perfect relationship, it means that all the values will be concordant. Okay, and so you find zeros here. You find zeros here, and you find non-zero values here. Okay, meaning that this will be going to 0, meaning that this will also be 0 if the discordants are 0. So you'll be taking a number or value divided by itself, which will give you positive 1. The same case, or you can find that everything is 0 here, but everything here is non-zero, meaning that this is what will go to 0. This will remain something, then this will go to 0 divided by that, meaning that you are going to end up with -1. So basically, that's what we call the Kendall's tau. The main objective is to see how to perform this in R. So I want us to go to R and perform this kind of analysis. So yeah, in R. So we shall be using a function corridor test, which will give us the Spearman's correlation coefficient or the Spearman's rank correlation coefficient, and also test whether it is significant. Okay, and just like we saw in the case of other non-parametric tests, there's always a problem in the computation of the p-values when you have ties in the data. Like in our data, there are some ties. So in such cases, you find that you cannot get the exact p-values. So let's run the test. Then the output is here. So now here we have the Spearman's rank correlation row. Then the name of the data is here. Then S, this S here is equivalent to what I was calling D squared in the slides. So this is our D squared, a summation of D squared, sorry. Then we have the p-value is this, which clearly shows that it is not significant. The alternative hypothesis that the true row is not equal to 0. So that means that our null hypothesis was that the true row is equal to 0. Then the value of rho, which is the Spearman's rank correlation coefficient, is this number here, 0.318002. And we are seeing that it is not significantly different from 0 because the p-value is quite small, And then there's this warning here that in corridor test default, this Spearman, if that's a method, cannot compute exact p-values because of ties. When we have ties, just like we did in the test for mean, when we have ties and we're using the non-parametric statistics, then this means that you cannot get an exact p-value, but this is the approximated value of the probability value. Okay, so as you can see here, the Spearman's rank correlation coefficient is not significant. Okay, so I want us quickly to obtain the Kendall's tau using a similar approach. So you just need to change the method in this formula. In this formula here, so I just copy this. Copy this. I'm doing it down here. I want to change the method here too. As you can see from here, you just change from here. So I just rename this. And I run the code. Okay. And again, we still have the same warning. This is called Kendall's rank correlation tau. Okay. So the data is the one we have used. Then the test statistic in this case is a Z. So there's a Z formula. There's a formula which converts the Kendall's tau into a standardized value, that's a Z. And the p-value corresponding to this Z value is 0.11, which is clearly not significant. The alternative hypothesis is the default value. And then the tau itself is 0.2350 and so on and so forth. And again, the same warning because we have some tied ranks. Because some ranks are tied, we have the same problem of obtaining this p-value. But clearly, as you can see, is that the p-value, when you use the non-parametric methods, is not significant. You can see here. And when you look at even the parametric method, that is when you use the Pearson's rank, the Pearson's method, using let me call this. If you use this function here, you use the Pearson's method using the corridor test. This is what I need. Corridor test. Yeah, this is what I need. So if you use the Pearson's method, you notice that the p-value is okay, it's less than 0.5, but it's very close, it's marginally significant. So it looks like the methods are almost agreeing that the correlation between blood glucose and short velocity is actually, the correlation is not different from zero. As you can see, the p-value is almost insignificant, though it's at the margin. But the other methods are showing that the correlation coefficient is actually not significant. So I want us to stop there, unless there's a question. Yeah, I want us to stop there. From next week, we shall be looking at the analysis of variance, and we shall be briefly talking about the parametric and the non-parametric methods that are used in the analysis of variance. So let's meet next week.